Okay, Physics Module 7, Uniform Circular Motion and Gravity. I will also take a picture and post my picture of my notes so you can use that maybe as you go along and read, since I won't have written notes or very, many written notes for you to follow. So this chapter is on uniform circular motion. So when things are spinning in a circle. I don't know if any of you have ever ridden the ride. I think it talks about it in here. We used to have one at Worlds of Fun where you would stand, it was like a cylinder, and you would stand on the floor and it would spin really, really fast. And then the floor would drop down. I mean, it only dropped down like that far, but you would stick to the sides. And that's because of uniform circular motion. So, what is uniform circular motion? It is moving in a circle at a constant speed. So you're moving in a circle, you're going at a constant speed. The sum of all your torques is going to be 0. It has non-zero acceleration because the direction changes. So because there's directional change, that's what makes our acceleration change. Okay, so if you look at figures 7.1 and 7.2, velocity is tangent to your circle as you're going around, and acceleration is pointing into the circle. Same thing with force. The velocity is going tangent to the circle, and the force goes into it. No net torque force, but there is a net force. Okay, so the difference between centripetal force and centripetal acceleration. Centripetal force is the force needed to make an object move in a circle. So, and it's going to be directed into the middle of the circle. The force goes into the middle of the circle. When you were spinning your things, this was centripetal force that we were doing. Centripetal acceleration. Acceleration caused by centripetal force. So, the acceleration is the acceleration caused by that centripetal force. Centripetal force is necessary for any kind of circular motion. So then we have our first equation, which is at the bottom of page 221. Force C, which is your centripetal force, equals mv squared over r. So, hold on, I have a board. I did bring a board in here. Okay. That did not help. I need to raise it up. Hold on, let's see if I can make you higher. Maybe not. Hold on. Okay. That worked. See how good I am? Okay. Force C is your mass, your velocity squared over r. So this is your centripetal force. This is your mass. That is your velocity. Or you're really going to be actually looking more at speed here because you're constantly changing direction, right? So, and then your r is your radius. So if something is spinning like this, the length of your string, if you have a string hanging off, is going to be your radius because that's half the circle, right? Okay. Got your page. Okay. And then we also can find the acceleration. Centripetal acceleration is going to be the speed squared divided by r. Okay. Let's look at example 7.1. We have a 151 gram toy truck that travels in a circular track whose radius is 1.1 meters. If the truck travels at a constant speed of 2.1 meters per second, what are the magnitudes of the centripetal force and acceleration? Okay, and the force, remember, is always just going to point into, so it tells you to draw a picture of, draw the centripetal force vector. The vector is just going to be going into. So you just use your equation here, and you plug in what you know, and you divide through, and you're able to find it's 0.61 newtons. And for the second one, you plug it in, and you're able to find 4.0 meters per second. One thing to note, remember, newtons is in kilograms, So you have to make sure your masses when you're doing these are also in kilograms. Okay, so don't forget that. Okay, source of centripetal force. And then we're going to look at page 224 and 225. So, I wrote this the other day. Tension in a spring. Okay. Hold on, I got to look real quick. What causes the centripetal force? Well, you might think the buoy does because we have this plane twirling it around. Ultimately, that is true because the plane would never travel in a circle without the buoy there. However, the buoy is not touching the plane. Therefore, he cannot exert a force on it. The force exerted on the plane comes from the string, comes from the tension in the string. Same thing when you have a bike going around in a circle. The force comes from the person riding the bike. Okay? So, we have example 7.2. One track and field event is called the hammer toss. In this event, the competitors twirl a mass on a rope and then release the rope, causing the mass to fly off in a direction that it was released. Suppose a competitor is twirling a 12 kilogram mass on the end of a 0.65 meter rope. If the tension of the rope is 2.1 times 10 to the third newtons, how fast is it moving? So because it gives us the tension is our force. Because the tension in that rope is the force. So if you turn your page to 226, you're able to see that you can put the force in there. You know the mass, again, make sure it's in kilograms, and you can solve through the problem. The second one on this is a little more tricky because it just starts to involve this friction that we've already done, and now we're back to doing more friction. A car is traveling down on a road which curves. The curve's radius is a curvature of 15.1 meters, and the coefficient of friction between the car's tire and the road is 0.34. What is the maximum? With what maximum speed can the car travel around the curve? Okay, so we are trying to find here a maximum speed that we can go. So we need to know the centripetal force. So we have to find the force. Hold on. Okay. So we can go ahead and find, okay, since we're not given the mass of the car, we cannot calculate the weight. Even though we can not get a number for the frictional force, we can go ahead and get an expression for it. Okay, so yeah, now I remember. Sorry, I did this. This is what happens when I do it too early, right? I forget. Okay, so we cannot fill in all of the friction formula here. Oh yeah, now I remember. You get to cross things out. This is fun. Okay, we have friction is mu normal force. Normal force is mass times the acceleration due to gravity, right? So the frictional force, which is what we need to find here, once we have the frictional force, we can plug it into our F equals mv squared over r to find our v. We know mu is 0.34, but we don't know the mass. So we're just going to leave it m, and we know acceleration due to gravity. So the friction, so right here we have 3.3 m. M is the mass, but we don't know it. So we have two variables. When you have two variables, you can still plug things in. So we're going to go back to our Fc equals mv squared over r equation. And we know Fc is going to be 3.3 m. We have mv squared. This is what we're trying to find. And we do know r is 15.1. Because we have m on both sides of the equation, they actually cancel out. And we're left with 3.3 equals v squared over 15.1. So you can multiply and then find the square root. So because they're on the same side of the equation here, the mass cancels out. So think of it this way, if that's throwing anybody off. If I have 3A equals 6A, my A's cancel, right? There's an A on each side. I can cancel them out. Okay. 3 does not equal 6, so. Okay. So. Okay. Physical science is doing similar things, just slightly less, so. Okay, on a flat curve, the mass of the car does not affect the speed at which it can stay on the curve. So the mass of the car is not going to matter. You could put any number in for the mass and it would cancel itself out. That's another way to think of it. When you're like, why can it cancel out? Well, we had 3.3 m equals mv squared over 15.1. It wouldn't matter what I put in for this m. The problem would solve exactly the same way. So if I put 1 in for the mass, I would still end up with 3.3 equals v squared over 15.1. If I put 2 in, all my numbers would be doubled. If I put 3 in, that's why it cancels out, like mathematically. So that's just algebra, right? Okay. You guys probably all understood that. I didn't have to keep going. Okay. If we increase the speed, we increase the friction needed. You have probably experienced that if you have driven out on these icy, awful roads in town. If you increase the speed, you need more friction. So slow down when you're driving through icy covered roads. Okay, frictional force. There is no thing called centrifugal force. So a centrifuge works because of Newton's first law, and it goes into a long explanation here about how the centrifuge actually works. It's really cool. Separate things based on density. And it has to do with that once you're in motion, you're going to stay in motion. So those objects just stay because they're going really, really fast. Think about if you're driving in a car and you hit your brakes, you go forward. Same thing when it stops. They're still kind of moving, and that helps them settle out. Okay, your book explains that pretty well. Okay. So there is nothing actually in science called centrifugal force. Gravity. Okay. We've talked about gravity. We've talked about things falling due to gravity. This is the attractive force of any two bodies that have mass. All objects exert gravity on each other. So, if I am standing here, me and my phone are exerting gravitational pull on each other. However, obviously it's not enough to attract anything. So, you also find out as you read your book that we don't actually know why this works, which is always a fun scientific explanation, right? So, the force of gravity is G, M1, M2 over R squared. So, this is the force of gravity. This is a constant. It is the universal gravitational constant. It is 6.67 times 10 to the negative 11th Newton meters squared over kilograms squared. This is mass of 1, mass of 2, and this is the distance between. I don't love that they use radius because it's not really a radius, it's a distance between. Okay? Who's opening my door? It's okay, I'm just doing a physics video. You can say hi. Okay. So, the more massive objects are, the more that they're going to exert a gravitational pull on each other. So
wait. If I put on some extra weight, that makes me more attractive to you?
I got nothing. They got nothing.
That was unplanned.
That was Scott's commentary. You're welcome. Okay. So, this is a weak force. It's obvious this is a weak force because we're not like constantly being pulled towards each other, right? Like it takes lots of mass, which is why planets can exert a gravitational force. Now, technically, because it does depend on the distance, if you are on top of a mountain, for instance, you're going to have slightly less gravitational force or gravitational pull than you would be standing at the lowest spot on Earth, like at sea level, for instance. So that does mean you might weigh slightly less if you go stand on top of a mountain. Okay. Circular motion. We are now on page 235. And Scott finally left. Okay. We have some terms. Period is the time it takes an object in uniform circular motion to travel one full circle. Frequency is the number of times per second an object in uniform circular motion travels around a circle. So, in 1 second, how many times does that object travel around the circle? Period is how long it takes. Okay, so we measure frequency in a unit called hertz. Hz. It's 1/second is what a hertz is. But we like to have lots of random things here, right? Okay. So, frequency is 1 over your period. So this is frequency. And this is the period or the time. So we have example 7.5. A hyperactive dog runs in a circle. The circle has a circumference of 2.2 meters. And the dog runs at a constant speed of 1.6 meters per second. What are the period and frequency of the dog's motion? In order to make a full circle, the dog has to travel 2.2 meters. If it is running with a speed of 1.6 meters per second, we can use our distance equals rate times time to find our time. And then once we have our time, we can plug it into our frequency equals 1 over t and find our frequency. Okay, gravity and planets. The sun's gravitational attraction to a planet supplies centripetal force to each planet, causing the planets to move in their circles. Okay. We have example 7.6. In this, how fast does Mars travel in its orbit around the sun? Oh yeah, I even already did the problems of these. I was like, hold on, did I do these? I did. Okay. So we know that the force of gravity is going to equal our centripetal force. We know that our gravitational force is G, M1, M2 over R squared. And we know our centripetal force is the mass of the one moving, V squared over R. We have lots of variables here. The nice thing is we can cancel them out. This is the mass of Mars. That is the mass of Mars. So we end up with G M2 over R. Actually, that R can cancel with that. So we still have one R here equals V squared. We can do some math and get down to finding V this way. Okay. The second part of it is, given the speed calculated in the previous problem, what is Mars's period of rotation? So we can find the circumference, which the circumference is going to be the distance that it travels, right? So if it's traveling, we want to know the distance it's traveled. Distance equals rate times time. So we find the circumference, which is 2 pi times the radius of the orbit. That's how we find the circumference, 2 pi times the radius. And then that becomes our distance, and we can find our time. Okay. 7.7. This is how scientists are able to find the mass of objects in space. We all know that the orbital period of Earth is 1 year, 3.2 times 10 to the 7 seconds. Using this fact and the fact that the radius of the Earth's orbit around the sun is 1.51 times 10 to the 11th meters, calculate the mass of the sun. Okay. So again, we are using this, and we get down to here. G, the mass of the sun, R equals V squared. Now, since we're trying to find this right here, we got to look at what we have already been given. We don't know the velocity. We know G and we know R from the problem, right? We're given the orbital period. So we're given that time, right? And we are given the radius. So we're given this, and we're given a time, and we're trying to find this. We know G, we know R, we don't know V, and we don't know M. But we can find V because velocity equals distance over time. And we know the distance and we know the time. Well, we don't know the distance, but we know the radius, and we can find it by doing circumference equals 2 pi r. This will give us our distance, and then we have our time. So these are actually, I found these kind of fun to work through. I mean, I'm not saying you'll find them fun. And once we have our velocity, we can plug it in and then work through and find our mass. Okay. Overall, those are the problems, and they're pretty straightforward, I think. So if you get stuck on any of the practice problems, I will try to leave time for us to go through any and see if we need to answer any of those. Okay? So do your very best, and we will finish going over anything we need to later.